All right, so should I get started now? Yes, okay. All right. So first of all, thank you for being here on a Saturday evening. My name is Tom Maccarone, and I'm going to talk about searching for black holes. And I'm going to talk about this in three parts. So one is I'm going to talk about the science that surrounds how we search for black holes in the Milky Way galaxy. And then I'm going to talk about how we design new observatories and satellites, which is something I've been involved with a bit. I haven't been involved with anything that's actually been built yet, but the process is quite lengthy, and I've been involved with the early stages of this. And then I'm going to talk about career development for aspiring astronomers. I'm mostly going to tell you about the path that I've followed, just so that you can see an example of what the steps are that you have to go through in order to end up with a career in this field. All right. So before we get into black holes and neutron stars, I want to talk about how stars evolve, just to kind of set the stage for this. So when we look at the stars in our own galaxy, we see that most of them fall along this branch here called the main sequence. And along this main sequence, stars are fusing hydrogen in their cores. And because of that, where they lie here depends only on their mass. So the highest mass stars are in the upper left, lowest mass stars are in the lower right. And then after a certain amount of time, if they run out of hydrogen in their cores, the stars can start to see their cores contract and their envelopes expand. And during this stage, they become these giants and supergiants. And at various points, while they're up in this part of the diagram, they may have fusion of elements heavier than hydrogen in their cores. Now, eventually, for the massive stars, the ones that are heavier than about 8 solar masses here, sorry, 8 solar masses would be around here, right? So for these stars, they'll end up fusing elements all the way up to iron. And iron is the most stable element in terms of nuclear physics that we have. And so once you produce iron, you can no longer produce energy by having fusion take place. And the result of that then is that the star continues to contract, and now there's no fusion energy to inject into the star to stop the collapse. And so these stars see their cores implode, and depending on the mass of the core and the mass of the outer part of the star outside the core, what will happen next is either the whole star collapses into a black hole, a big fraction of the star collapses into a black hole, or the core's collapse injects the gravitational energy gets released when the core collapses, and that energy can get injected some way that we still don't actually understand very well into the envelope, blow the envelope of the star out, it produces a supernova explosion, and leave behind a neutron star. And so this diagram here illustrates the life cycles of stars of different masses. And so what we'll be talking about is what happens for these stars that are in this mass range and up. All right, and for the very most massive stars, you may get something called a pair instability supernova, where the core of the star gets so hot that pairs of electrons and positrons are produced, and the pressure from those blows up the entire thing and doesn't leave any remnant behind. All right, so now we've kind of set the stage for understanding how black holes can get produced in stellar evolution. And the general thought is that stars from about 8 to about 30 solar masses end up producing neutron stars, and stars heavier than about 30 solar masses end up producing black holes. This is something that people are still trying to understand fully. There's some debate about whether the boundaries are that solid, or whether there's different probabilities of producing black holes and neutron stars all along this range. All right, but for the most part, we know that massive stars produce black holes and neutron stars. And then the question is, how do we go about looking for those? And I'm going to focus on how we go about looking for the black holes, because those are harder to find. Right? So the basic idea of a black hole is that it's an object whose gravitational field is so strong that light can't escape from it. And as a result of that, you might think there's no way to detect them. But it turns out if you put a black hole in a binary system, you have a few different ways that you can go and look for it. Okay, so there's this famous quote among astronomers that 3 out of every 2 stars are in binaries. And the idea behind this is that if you look at 2 stars on the sky, you actually have 3 stars, because roughly 50% of the stars that you look at will be binary systems. Right, and so this is something that in the part of the world where you're all from, probably the earliest advance was actually made. So there's a star called Algol, which was known by the early Arabic astronomers. So as I'm sure a lot of you know, the brightest stars in the skies have Arabic names in every language. And Algol, the name, of course, means the demon star. And the thinking of historians of astronomy is that people were disturbed by this star because they noticed that it was variable. No other stars in the sky are obviously variable to naked eye astronomers. It was first written down that it was variable in 1667 by Gemignano Montanelli, who was an Italian astronomer, but probably it was known much earlier than that. Okay, and then in 1783, a guy named John Goodricke found that the variability of the star was periodic, and then that eventually turned into the proof that this was an actual binary star. Also in the late 1700s, a guy named John Mitchell, and John Mitchell was also the first person who came up with the idea of black holes. Mitchell made one of the first applications of statistics to astronomy, and he showed that there are too many close pairs of stars in star clusters for this to happen by chance. So he looked at a few nearby star clusters, and he saw, and he looked at the separation between the closest star and closest other star. And he found that there were too many cases where the 2 stars were very close to one another to explain at random chance. And he suggested that there were binary stars based on that evidence. Okay, so now what happens if we put a black hole in a binary system? Well, it depends how close the binary system is, so how tight the orbit is. But if you have a very short orbital period binary system, what can happen is what's illustrated in this cartoon here. That you have a black hole sitting here, and then you have its companion star sitting here. And if the companion star is close enough, its shape can be distorted. So you can see this is no longer a sphere, but instead it has kind of this teardrop shape. And the reason for this is the tidal force from the black hole on this star. And if you want an illustration of tidal forces that happens more nearby to us, you can look at the Earth-Moon system. So many of you probably know that the moon always shows the same face towards us. But what I think a lot of people don't appreciate is why that's the case. And the reason is that the moon is not quite spherically symmetric. The moon is elongated and pointed towards us. And because of that, it gets forced to align with us. And we call this process tidal locking. The tides on the Earth are trying to force the Earth to align with the moon. And that's why the length of the day is gradually getting longer over time. So eventually, I don't know how many billion years from now, but very far in the future, the rotation period of the Earth, the rotation period of the moon, and the orbital period of the moon around the Earth should all become the same value. I think the sun will actually expand and swallow us up before that actually happens. But we're working towards that because the tidal forces have worked a lot more effectively on the moon than they work on the Earth. All right, so when the star gets to this kind of configuration, at this point, which we call the inner Lagrange point, the gravitational attraction of the gas that's sitting right here is the same towards the center of the star and towards the black hole. And so what that means is that because there's some gas pressure, some of this gas ends up getting spilled off of this star and flowing towards the black hole. All right, now what you would then expect to happen is that you would form an orbit at the place where the angular momentum of this gas is equal to the angular momentum of a circular orbit. And so your quick expectation from what you might learn in a first physics course would just be that you get a circular orbit of the gas around the black hole, and it would just sit there. But what happens then is that you end up with a process that's something like viscosity. So fluid exerting a friction on other fluid. And that causes some of the gas to fall in, and some of it actually has to get ejected, but most of it falls inwards. And it gradually spirals in towards the black hole. And as it does that, it's losing gravitational energy, right? Because it's falling. And that gravitational energy goes into heating up this disk of material. And so as a result, because the gravitational potential well for a black hole is so deep, you end up getting this gas to become very hot. So typically, it'll reach temperatures of about 10 million degrees Kelvin. And at a temperature of 10 million degrees Kelvin, an object will emit X-rays, right? So if you think about, like, our sun is a few thousand degrees Kelvin, so 5,800 degrees Kelvin. And at those temperatures, it mostly emits optical and infrared light. And when you get up to temperatures that are around 2,000 times higher than that, the energies of the photons will typically be 2,000 times higher, and that makes them X-rays. Okay, and there are not very many things in the sky other than these kinds of binary systems that are really strong sources of X-rays. And so if we go and we look for sources of X-rays in the sky, we have a pretty good chance that we're going to find an accreting black hole. One of the other things that we could do is if we put a neutron star in the middle of this disk, everything would look almost the same. So the neutron star is a little bit less massive than a black hole. So the black holes that we see in our Milky Way galaxy tend to be about 5 to 20 solar masses. Neutron stars tend to be about 1.4 solar masses. But the event horizon around the black hole, which is kind of the last place from which light can escape and still carry energy away, that's further away from the center of the black hole than the surface of the neutron star is from the surface of the neutron star. So the potential wells are essentially the same for the purposes that we're interested in here. Okay, so this now is an X-ray image of the entire sky. And this was taken from one of the early NASA satellites. Sorry, do we have a question in the chat window? Oh, yeah, okay. All right, yeah. So if you have, if you look at this X-ray map of the whole sky, you can see that this map is made not exactly how it would look on the sky, but instead somebody took the coordinates and transformed them so that the plane of the Milky Way galaxy is sitting here. And then this is, these directions are out of the plane and these directions are along the plane. And so one of the things that you can see is that here in the center of the Milky Way galaxy, you have a very strong concentration of sources. And even away from the center, an awful lot of the sources are in the plane of the Milky Way galaxy. And most of these sources that are sitting in the Milky Way galaxy here are accreting black holes and accreting neutron stars. As you go out of the plane of the galaxy, some of them are still accreting black holes and accreting neutron stars in our own galaxy. But now some of these objects will also be supermassive black holes at the centers of other galaxies. And I think these objects here are the Magellanic Clouds, which are the nearest other galaxies. All right, and this is from a map that was made in the 1970s. So we can do much better now, but it turns out that if you make a much deeper image, you still don't see much more without zooming in on the faint objects. So I like this image. It's a nice looking one. So, so in our Milky Way galaxy, we expect that there may be 1,000 to 10,000 of these binary systems with black holes. And at the present time, we know about 50 of them. And one of the issues is that if we look at these accretion disks, it turns out that the gas doesn't flow in smoothly. It tends to build up for a while until it gets hot enough and then dump a whole bunch of material all at once. And so these systems are what we call X-ray transients, and they tend to have outbursts every few years to few centuries. And so there are probably a whole bunch of them that we just haven't discovered yet because they haven't had one of the outbursts during the amount of time over which people have been doing X-ray astronomy. All right, so now I'm going to talk about doing astronomy from space and why it's important for X-ray astronomy and why it's hard to do and what the process is that we go about, at least on the NASA side, which is what I'm familiar with, in order to get a space mission approved. Okay, so this first plot here is a plot of the opacity of the atmosphere as a function of wavelength. And so what we can see is if the opacity is 100%, that means the light doesn't get through the atmosphere. If the opacity is 0, that means all of the light makes it through the atmosphere with no absorption at all. And if it's something in between, it means some of the light will get absorbed on the way to us, but varying fractions. All right. And this plot really illustrates very well which kinds of astronomy we tend to do from the ground and which kinds of astronomy we tend to do from space. So obviously the earliest astronomy that humans have done has been optical astronomy, and that's in this blue through red band. And we can see the opacity is pretty small here, so around 10 to 20%. And obviously if it weren't, we wouldn't be able to see. And so that's one of the sorry, page up. All right, and so that's one of the important historical points there. And then as we go to the infrared band, which is the radio band, so in the radio band, the atmospheric opacity is basically 0, so everything comes through quite well, but we can't observe radio waves with our eyes, and it in fact took some decent advances in electronics before we were able to build radio telescopes that worked. But now we could do that really well from the ground. And then if we go to the infrared band, we see these windows in the infrared band where we can look, and then other windows where we can't. And that's because the main thing that absorbs light in the infrared band is water vapor. And so if you're places where water vapor has a molecular transition, then you're going to have a very high opacity. And if you're places where water vapor doesn't have transmissions, then you're going to have low opacity. And that's also an argument for putting telescopes on high dry sites. It enables you to get up above more of the atmosphere and to have less water vapor in the little bit of atmosphere that you're looking through. And so this is why we have telescopes on desert mountains. All right, so this tells us that for certain kinds of astronomy, like far ultraviolet, X-ray, and gamma ray astronomy, we have to do it from space. Also for very long wavelength infrared astronomy, we have to do it from space. Okay, so otherwise we prefer not to do things from space because doing astronomy from space is very expensive, right? And there's a whole bunch of reasons why it's so challenging to do astronomy from space. One is that you have to have rockets that are good enough to launch the telescope that you want to use. And that often limits the size of the telescope that you can build. And then you also really have to have everything working properly before you launch it. If you do something on the ground and you make one little mistake, you can fix it. In space, the Hubble Space Telescope has been repaired a few times, so it's not impossible, but it's extremely expensive and a little bit dangerous. All right, so now let's talk about the reasons why you might do astronomy from space, though. So one is this one, that you can't see through the atmosphere at certain wavelengths of light. Another one is the atmosphere distorts images. So of course the Hubble Space Telescope and a few other optical telescopes are flying in space, even though they're observing wavelengths of light that we can observe from the ground. And the key there is that as light passes through the atmosphere, its path doesn't follow an exact straight line because it's no longer going through a vacuum. And if we go into space, we can get above the atmosphere, and so we can make sharper images than we can make from the ground. Another one is that the background radiation on the surface of the Earth can be too large for certain bands. So in the infrared bands, the light gets through, but say, like if we look at 10 microns here, the opacity here is really small, right? And people sometimes try to do 10 micron astronomy from the ground, but it's actually really hard. And the reason is that for a temperature of about 300 degrees Kelvin, like what we have on the surface of the Earth and of every other object on Earth, including your telescope, the main wavelength of light that gets emitted is around 10 microns. And so what that means is that the background radiation on Earth is extremely high, almost no matter how effective you are at cooling all of the key parts in your system. And so that's so you can observe very bright sources from the surface of the Earth very effectively in that wavelength range. But if you want to observe faint sources, you have to go to space. one other thing is there's a little bit of radio astronomy that gets done from space, and that gets done so that you can separate your telescopes by more than you can separate them on the ground. Radio telescopes tend to work in arrays where you combine the data from many telescopes, and that allows you to get the same image quality that you would get from one giant telescope. So if you want your giant telescope to effectively have a size that's many times the size of the Earth, you have to go to space. And one other thing is that sometimes you want to do continuous observations of sources. And for example, if you're familiar with the Kepler or TESS missions that search for planets transiting in front of stars, that gets done from space because if you want to continuously observe the same part of the sky, you can't do that from the ground because the Earth rotates. You could observe a few parts of the sky for 6 months of the year from the South Pole, but going to the South Pole is almost as expensive as going to space. All right. So now I'm going to talk about mission development a little bit, and I'm going to talk about this from the perspective of a satellite where I was working on the project. Right now we have a concept for a mission, and we hope to propose this mission to NASA within the next couple of years. But like I mentioned before, this is a very long process to go from an idea for a satellite to an actual satellite. So the satellite idea we have is something called Strobe-X, and this is for looking at the variability of X-ray sources in the sky. And it has 3 instruments on it. So one is an all-sky survey instrument, which it would sit here. And then sitting here, we have 2 pointed instruments. Sorry, one is here and one's here. So this one is a high-energy X-ray instrument, and this is a low-energy X-ray instrument. And the idea is we would have about 10 square meters of X-ray detectors on this satellite. And that would enable us to have very good sensitivity to variations of bright X-ray sources. And since we want to look at bright X-ray sources, we don't care so much about the background. And this satellite would be a lot cheaper than building a 10 square meter satellite that was aimed at looking at faint sources, because if you want to look at faint sources, you also need to have very good image quality. And so there are always these trade-offs that you have to make when you're designing a satellite mission to do some interesting science within a reasonable budget. All right, and so then this here would be what we call the bus for the satellite. This would be the antenna that sends the data back to Earth. And these here would be the solar panels. And this is actually a key thing to bear in mind, is that you have no source of power for most satellites other than the sun. And so solar power ends up being a key driver for how much power your satellite can operate on. And so one of the important things for advancing satellite astronomy has actually been advancing the capabilities of solar panels. You can have some batteries on the satellite that store some solar power so that when you're, like the satellite will end up being in a low Earth orbit, so it'll go behind the Earth so that it won't be detecting the sun at various points in its orbit. So you can have batteries for that kind of purpose, but you can't have batteries that'll last the whole lifetime of the mission. All right, so the things to think about when developing a space mission. So first of all, the technology has to work the first time. On the ground, like I mentioned before, if you have a loose screw, you can bring a screwdriver and tighten it. If you have to do that in space, you can only do that for satellites that are in certain kinds of orbit. And even then, it costs hundreds of millions of dollars to do that. That's essentially the cost of a space shuttle launch or equivalent other launch. And so this gets really expensive. And so people tend not to fix satellites. The Hubble is the only one that's ever been fixed. The other thing to think about is the cost of the satellite, but also the mass of the satellite. Because the satellite has to be low enough mass that you can fit it into a rocket and get it into the orbit that you want it to be in. And so for some kinds of satellites, putting it in what we call a low Earth orbit, so an orbit that goes where it goes around the Earth roughly every hour and a half, that's good, and that allows you to have a higher mass with the same rocket. But there's some other cases where you want the orbit of the satellite to be much further away from the Earth. And so infrared astronomy satellites are a good example of this because you want to get them away from the glow of the Earth. And those ones then have to be even lighter to use the same rockets because you need to use more power to launch the satellite up to a higher orbit. Okay, next thing is if there are multiple things that are on the same satellite, they should work together. The reason for this is that a lot of times you have to choose which instrument you're using. And even if you don't, you're paying to put these things on the same satellite. And so if you have something that you end up using only 10% of the time, you might be investing a huge amount of cost in that instrument without getting much value out of it. And so thinking about how to have a science case that takes advantage of all of the different instruments that you put on the satellite is really important. And then the other thing to think about is that the competition for getting the right to build a satellite is pretty intense. This is at least for the big space missions. There are actually some programs for small satellites and CubeSats where it's pretty easy to get them launched. And that's something that you all might want to start thinking about as a club is there some kind of CubeSat that you could build and launch into space? So the idea behind these CubeSats is that when they're launching commercial satellites and rockets, usually the commercial satellite doesn't fill the whole amount of space that's in the rocket. And so if you can build something that's, say half a meter cube, you can fit it in the empty space and they'll throw it out there for you. And there are some ideas that people have had about actual interesting scientific projects that you can do on a low budget that can be done that way. All right, so now I'm going to talk about my career path. So I did my undergraduate degree in physics rather than astronomy at the California Institute of Technology. And so one of the things I'm going to say is that if you want to be an astronomer, you need to get a really strong physics background first, because an awful lot of what you do in astronomy is applying physics to the universe. So it's important both to have a general knowledge of astronomy phenomena, but also to know enough physics so that you know how to solve the problems that you end up coming up with. All right, and now I want to talk about how to think about science as a student. So make sure that you're questioning everything, and so solving homework problems that you get in class is important, but what's just as important is understanding the assumptions that go into the problems that you're solving. So think about why what you're doing works and not just how to get the right answer. And if you always keep asking questions, why do we believe that this is true? So, if somebody tells me that gravitational acceleration gives me distance change that's 1/2 GT squared, why is that true? Right? So always be asking these kinds of questions as you're taking classes, and that will help you think about things the way real scientists do rather than early stage science students do. Okay, and then the other thing I would say is that the key advantages in science require imagination and curiosity as much as they require technical skill. One of the things I want to kind of bring up as an example of this here is how many of you all have heard of Albert Einstein? You can put in the chat window, yes, if you've heard of him. Or you put no, yeah, yes. All right, is there anybody who hasn't, right? All right, okay, so everybody's heard of Einstein, of course, right? How many of you have heard of Marcel Grossman? So put a yes or a no, depending on whether you've heard of Grossman. Okay, so a lot of you haven't heard of Marcel Grossman. Right, so now let's talk about both of these, because both of them were very important in developing the general theory of relativity, which is, of course, the theory that tells us that we should have an expanding universe and that we should have black holes. Okay, so Einstein and Grossman were friends from time they were young. Einstein came up with these ideas about how gravity should work under a theory of relativity. So the whole basis of the theory of relativity, there's the special theory, which is fairly easy to learn because you can do most of that with just high school algebra. And the special theory deals with relativity without acceleration. And then there's a general theory of relativity, which deals with relativity with acceleration. And so what Einstein did to develop these theories is he started with the assumption that physics should be the same in all reference frames. So no matter how you're moving or accelerated, the laws of physics should look the same for you. And then he started with the idea that the speed of light in a vacuum was a constant and the fastest speed possible in the universe. Okay, and then what Einstein did next was he developed these thought experiments where he said, okay, let's think about different scenarios that we might produce that would allow us to figure out what the real laws of physics are and how to change Newton's laws of physics to meet these two conditions. Okay. So for the special theory of relativity, Einstein just went and he did this. When he started doing the general theory of relativity, he was able to set up these thought experiments and think about what equations you could solve, but Einstein didn't actually know enough math to solve these equations. And so he had to go to Marcel Grossmann, who was an expert in the right kinds of math that were needed to solve these equations. And Grossmann helped him figure it out. All right, and now the reason I'm bringing this story up is that we all know who Einstein is. And I think maybe a third of you had heard of Marcel Grossmann. Right, so what was important here? What was important here was developing these thought experiments, having the curiosity and the imagination to think about the right questions to ask and the right way to ask the questions. It was also important to be able to answer the questions correctly. But if Einstein hadn't found Grossmann to help him with that, he may have found someone else to help him with that. Right? There were a lot of people like Grossmann around whom Einstein could have spoken to. So as a result of it, Einstein is the one who we think of as the real genius behind developing the theory of relativity, and I think correctly so. Grossmann, of course, played a very important role in developing this theory, but a more secondary one. All right, I have a question in here that I think that somebody sent to me, and I'll answer that after I'm done because I think that's a long question. All right, so then after I did my bachelor's degree, I went to graduate school and I got my master's and PhD from Yale University. So if you want to be a professional researcher in astronomy, this almost always requires a PhD. You can find, a few dozen people around the world who don't have PhDs. In a few countries where PhDs weren't a standard degree until the 1980s, you can find a lot more, but you're not seeing any new people coming along in those countries who don't have PhDs. So some other aspects of doing things in space, especially on like the satellite launching and rocket development side, a lot of the people in those areas have bachelor's degrees in engineering and then go work for a company. And so if you don't want to go through this very long period of education, but you want to be involved in space, there are ways to go about doing that. All right. And so then after my PhD, I went and I did 2 postdoctoral fellowships, one at the International School for Advanced Studies in Trieste, Italy, and the other one at the University of Amsterdam. And so I think when I was the age you all were, I didn't really know what a postdoc was, but a postdoctoral researcher is somebody who is working on their own research projects full time, but isn't the head of a research group. And so it's usually a position that you do for 2 or 3 years at a time, and then move to another institution. And so this is a period where you can really focus on your own research and grow in independence as a researcher. And if you want to become a physics or astronomy professor in research intensive universities in most Western countries, you need to do a PhD. There are some countries, like I think we've had some PhD students from Saudi Arabia who came to Texas Tech, and at least one of them went straight back to a faculty position in Saudi Arabia after the PhD. That guy was doing condensed matter physics. And so there are possibilities in some countries to skip the postdoctoral period, but if you really want to develop yourself fully as a researcher, it's an important time. All right, and so then I've had 2 faculty positions after that. So first I was at the University of Southampton in England, And then about 8 years ago, I moved to Texas Tech University to help start up our astrophysics program. And now, one other thing I want to say is I'd like to encourage you all to try to start getting Saudi Arabia towards thinking about having a space program. It's a wealthy, high population country, so there are plenty of resources in the country to do these things. If you want to do everything that a space program can do, there's really 3 countries right now that are at one level, which are the United States, Russia, and Japan. And then the European Space Agency, as a kind of group of Western European countries, is also kind of at the same level. And then the countries that are lower population, less than 100 million people, generally have niches where they do things, but don't try to do everything all across the boards, because it is very expensive to have a full space program in a country. So there are kind of 2 aspects of space programs. So one is launching things, so developing the rocket technology. And the other one is making the hardware that goes on the rockets. And a lot of the smaller countries have started off with the space hardware or with small rocket programs, and gradually developed bigger rocket programs. So like in India, for example, they have a good emerging space program there. They have their first astronomy satellite going right now. It's something called Astrosat. But the Indian X-ray astronomy community had a history of doing things with balloon launches for quite a long time, so that they would learn how to make hardware that works in space. So with balloons, you can get up into the very upper atmosphere, and you can do a lot of the same things with balloons that you would do with rockets. And the disadvantage is that the balloon flights tend not to last as long, and they don't go up quite as high. But they're a good way to test out hardware so that you get your equipment back, and you can try to fix things and see if you can get them to work better the next time. And so a lot of the countries that aren't quite as big as the United States, Russia, and Japan have started off by building instruments that go on satellites that are launched by the major space agencies around the world. And so that may be something that you folks might be interested in getting started. All right, and so now I'll be happy to take some questions. So I've got 2 questions that came to me in the chat already. Before I go on and answer these, Naran, is that how you want me to answer them? And by the way, I hope I pronounced your name right.
Thank you so much, Professor, for taking the time out of your day to come speak with us today. We really appreciate it.
Okay, you're welcome. Thank you.
And I received many questions privately. You can answer the questions you received, and then I will inform you of the ones I received.
Okay, so the first one I got was, when did you discover your passion for physics? At what age? And what did you do outside school curriculum to develop your physics knowledge? And what advice can you give me as a 15-year-old Muslim hijabi who wants to have a future at NASA? Okay, so that's 3 questions. Let me start with the first one. When did I discover my passion for physics? So this was a gradual process for me. So one thing is, my father was a high school physics teacher, and so he would sometimes show me things at home, and I would learn some things from him. And in terms of what I did outside school curriculum, so when I was in high school, I did math and science competitions, and that was the main thing I did at that stage. And I would also read a lot of popular science books at that age. And what advice can I give you if you want to have a future at NASA? So one thing I will say here is NASA only hires American citizens as civil servants. So the permanent staff positions at NASA require US citizenship. There are some other kinds of jobs where you could effectively work at NASA, where you don't have to be an American citizen. And then there are a lot of other jobs doing science using NASA facilities where you don't work for NASA, and that don't require American citizenship. If you really have your heart set on working for NASA directly, you have to move to the United States and become a naturalized American citizen. And if you're the immigration process to the United States is it's a lot of paperwork and it can be annoying, but for people who have advanced degrees in science and engineering. There are no limits to the number of people that can come in, and there's a special category for permanent residency. I'm not sure about some of the other national space agencies about whether they require citizenship to work there. I don't think the European Space Agency does. All right, so I have two related questions from the same person. So one is, if I want to be an astronaut, is astronomy the best major for me? Or and same person says, I'm planning on taking aerospace engineering. So yeah, so I think if you want to be an astronaut, I'd say this. I don't understand this process fully because I've never tried it myself, but I've talked to a few people about it, and I think there's kind of two routes that you can take to becoming an astronaut. One is to be a pilot, and if you're a very experienced pilot, then you can get in on kind of that side of things. And then the other one is being a payload specialist. The payload specialists are the people who understand the instrument that's being deployed in space. And for being a payload specialist, I would say physics, aerospace engineering, chemical engineering is often a case too, and geology are good majors. So like if you want to be one of the astronauts who goes to Mars, which may happen at a time in the future that you all are young enough to think about doing, then you'd probably actually want to study planetary science or geology. If you want to be an astronaut who helps install satellites in space, then probably physics or astronomy would be more relevant. Increasingly too, especially with things like the space station, they're starting to do biology experiments in space. So almost any area of science can be good for that. Okay, now I have a question. Does NASA have any ideas of going deeper into the Milky Way? And so I think what you mean is launching explorers that would go out of the solar system. Is that right? The person who asked that question, could you tell me if I understand your question correctly? Okay, so I'm going to assume that that's what you're asking and answer that question. So I don't think any space agency has any real plans to go outside the solar system. So we do have the Voyager satellites that were launched in the 1970s, and they just keep going. And they seem to have gotten outside the region where the solar wind is really important. Excuse me. If you think about like sending a mission to another star, actually, now that I think about it, there's this Russian billionaire who wants to build a thing to send a mission to another star, and I'm not really sure what the point of doing that is, because the issue is that not only do you have to get data, but you have to be able to transmit the data back. And if you don't have a good source of energy and a good radio telescope to send the data back, you might be able to send a satellite somewhere, but you won't really be able to do anything with it. So this is something with future technology, this may start to become interesting. But the other thing is, if you think about it, the nearest star to us is about 3 light years away. And so if you want to send a satellite to that star, and you want to do it in less than a decade, that satellite's going to have to move at very close to the speed of light, and we'd have to figure out a way to do that. Okay, so the next question I have is, how is life as an astronomer? So I'm gonna, I guess, well, I'll say is, I can tell you what I do most of my day. So most of my day, so I'm a professor, and then I do research as part of my job. So probably during the school year, about half of my time is spent doing various kinds of teaching. And some of that is standing up in front of a classroom and teaching a class. Some of that is working with student researchers and helping them learn techniques. And then when I'm doing research, I spend a lot of time doing various kinds of things: data analysis, writing scientific papers, and then writing proposals to work on new data. All right, so next question I'm going to answer, can anyone try a project at the sky or do they need permission for it? So this is a great question. So almost all of the major astronomy research facilities right now have what are called public data archives. And so if you go to the NASA websites and look for something, I'm going to type into the chat window. KESARC and MAST. Okay, and those two things are archives of data analysis, of data taken from different NASA satellites. And most of the ground-based optical telescopes that are really big and powerful, run by the major national facilities, also have archives. And so you can go and you can work on data anytime you want. Now, if you want to tell NASA to point a satellite at some point on the sky, then you need to write a proposal. When you write the proposal, it'll go to a panel of experts that will evaluate the proposal. And usually 3 or 4 times as many people want to use the satellite as there is time available. And so then they try to pick the best proposals. You know, everybody has their own biases about what they think is most interesting and will work most effectively. And so sometimes you can submit exactly the same proposal the next year after it gets rejected and it'll get accepted. You know, there's a lot of competition there and it's hard to judge what the competition will be. All right. Okay. So let me see. All right, so I have one more question about astronauts. So sorry, one more question. As an astronaut who stays up 6 months on the ISS to do experiments and study the universe, what is the major that can lead me to such a future? So I think that an awful lot of majors could do that. And my guess is actually biology would be a really good one right now, just because I think there are fewer people that want to do biology that that want to go into space that study biology, there are a lot. If you're talking about the space station, one of the unique things it has is that you can do 6-month-long biology experiments up there. But there's also, I think, a bunch of areas of physics and engineering that will work out fine for that too. And if you want your backup plan to involve space, those might work out better for you. And I would say try to find a few other people to ask this question to too. All right, next one. Do you see studying astronomy as hard and complex as other people? So I think this is actually a good question, because I think a lot of times people think of physics and math and astronomy as being really hard subjects. And I think, in fact, what the case is that in some ways, they're really easy subjects because you know, in math, pure logic works. In physics, for the most part, we can break things down into very simple systems, and then they always behave exactly the same way once we've done that. And so as a result, doing research in these fields is in some ways easier than doing research in something like biology, where no matter what you do, everything is going to be really complicated. But as a result of that, over the 500 or so years since Galileo, we've learned an awful lot of physics. In order to make progress, you have to learn everything that people learned in the previous 500 years. And in the fields that are harder to make progress in, like biology or the social sciences, there's less that you have to master in order to make advances. So yeah, I would say biological systems are much, somebody said, so the question was, so bio is more complex. So I would say biological systems are much more complex than physics systems. But as a result, we haven't developed the same depth of understanding. Right, so it's easier to learn enough to make the next step forward, but it's harder to make the next step forward. All right, so now I've got a few more complicated questions in here. All right. Okay, so one of the questions is, what do you think has been the most important addition to astronomy that has led to the most progress specifically in your research field? All right, so that's kind of a tricky question to ask. So if you think about it, like on the whole history of astronomy timescales, I would say in my field, the most important development is the development of the ability to do astronomy from space. And so, yeah, I think I'll just kind of leave it with that point. All right. All right. What is the discovery you most anticipate making with your research, and what do you think it will change for science and for our world? So this is one of the things about research, is that it's really hard to anticipate anything. So I'm actually going to just decline to answer that question, because I don't like to try to predict the future in that way. So I'm sorry about that. Okay, next question. If a gamma ray burst is less than 10 light years away, would it affect the Earth? So that would depend. So gamma ray bursts are a particular class of explosion from stars. And what happens is probably the whole star explodes, but a small amount of the matter gets ejected along a jet, and that jet is moving it very close to the speed of light. And when things are moving at very close to the speed of light, instead of the light expanding away from the object spherically, it goes along the direction of motion. So if a gamma ray burst were pointed at us and it were less than 10 light years away, it would have a very dramatic and negative effect on life on Earth. It would probably strip the atmosphere off of the Earth and probably cause a mass extinction. If the jet were not pointed at us, you would still be having a supernova really close by, and I think that would still be a problem, but it wouldn't be as big a problem as the gamma ray burst. All right, so what was your most interesting research? So I would say the biggest discovery I feel like I've made in my career was the discovery of black holes in globular star clusters. So globular clusters are these big balls of stars that have around 1 million stars in a size scale that's about the same as the distance between the sun and the nearest other star. And so in these environments, you can get dynamical interactions between stars, and you can even sometimes have direct collisions between stars. And starting in the early 1990s, there had been some theoretical work that said that these clusters shouldn't have black holes. But in the late 2000s, I found the first really good example of one of these objects. And since then, over the last few years, this has become even more exciting, because with gravitational waves, people have started to find merging black holes that probably are merging in star clusters. And so that's the thing I'm most proud about. Is there a way to read the research? I'm really interested, actually. So yes, so there's so there's one website that you can go to called NASA ADS. And if you go to that, oh, sorry, I put that in the, I meant to put that in the chat for everyone. I'm gonna type that in again, NASA ADS. So if you go to that website, if you Google that, something will come up, and you can search for journal articles in there by author or keyword. And sometimes the journal articles will be hidden behind a paywall, only for people who have a subscription to the journal. But usually people put a version of the same paper on that site called Archive. And that'll usually be the same paper, but with a few typographical errors left in, because it hasn't been through the whole journal publication process yet. And so that's a good way to go and read journal articles. All right. Now we have a couple of questions. What would happen if a huge comet, meteor, or asteroid hit the moon and made the moon come much closer to Earth? Would that affect life on Earth? What would happen to the gravitational pull? Okay, so you have to think about that. It depends how much closer. If the moon came a little bit closer, I don't think it would affect very much. But of course, it would change the length of a month. And some biological creatures seem to have some natural rhythms that are associated with the length of the month. And it would also change the heights of tides. And so that actually probably it would then mean that the moon would no longer be synced in its rotation and orbit. And that actually might make the tides become very irregular. I think that would probably be the most noticeable effect, but I haven't thought about that problem very much, and there might be more interesting things going on. All right, next question. Is it true that there's a possibility of finding living creatures beyond the Earth? So I would say that there's a possibility of that. I would say almost all professional astronomers agree that that's possible. And the question, there's a couple of questions are, one is how hard is it to produce life on different planets? And there's a lot of debate about how special the conditions in the solar system are and on Earth. And then the other one is how hard it would be to find life on another planet. Okay, so first, let's talk about how you might go about establishing life on other planets. So there's some hints of life on Mars already, and this is just microbial life, like little bacteria. And this has come basically every once in a while, an asteroid or comet or something hits the moon and knocks a little piece off, and it ends up on Earth. And if it ends up at the South Pole under a bunch of snow and ice, it could get preserved pretty well. And so people have looked at some rocks that were found at the South Pole, and in a microscope, you can see kind of little cavities that look like bacteria might have made them. So that doesn't mean that life was, it could be that those samples got contaminated on Earth, and it could be that there is life on Mars, but it came from the same process, an asteroid knocking a little piece of the Earth off, bringing some bacteria to Mars, and then, another 100 million years later, it got sent back. So we don't really know in that case. Now, if we talk about outside the solar system, how we would look for life, this isn't my primary area of expertise, but I can give you the basic picture. There's a couple of different techniques that people have in mind. So one is that if you have a planet that goes in front of a star, you can look at the light from the star going through the planet's atmosphere. And if you see oxygen in the atmosphere of that planet, it was probably produced by living creatures, although there are probably some other ways that you can do that. But that's one of the signatures that people want to look for. And then the other thing is to look for what people call technosignatures. So signatures of actual technology outside the solar system. And one of the big ideas there is you could look for radio transmissions from another planet. And that's kind of a hard thing to do with the technology that we have right now. But we sometimes point our radio telescopes out and transmit signals. Excuse me. And so that it may be that an alien civilization will do the same thing. Yeah, so I still have a few more questions that were sent to me privately, but Nuran, if you want to send me yours, that might be good, because it's probably different people that are sending the questions to you, and I'd like to spread the answers around. So yeah, if you could send me some of the questions you have, that would be great.
What is it like to be a professor? And in your opinion, what are the pros and cons?
Okay, so I kind of answered that question a little bit earlier. You end up, so I would say the most fun thing is that you get to work with young, people who are excited about learning. And that's one of the big things. And then the other one is that you get to think of your own research questions that you want to work on. So I think those are the big pros. So I'd say the big cons are that if you compare it with doing certain kinds of research in companies that are trying to make a profit, if you're excited about the kind of work they do, they usually pay a little bit better, and they usually have more resources available for doing what you want to do. Now, I sometimes find it fun to try to solve a problem with just barely enough resources. And it can almost be boring because it gets too easy if somebody gives you everything that you need to do something. Okay.
What was it like, in your opinion, studying at Yale? And do you feel an education at an Ivy League university is higher quality than a state university?
Okay, so that's a good question. So so I studied at Caltech and Yale, and then since then I've only worked in public institutions, first in Europe and now in the United States. What I would say is I feel like Caltech, where I was an undergrad, really is very different from almost anywhere else, because the coursework is a lot more intensive. I would say when I went to Yale, I didn't find that the coursework that I was a teaching assistant for, or that were courses that had at a similar level to the ones that I teach at Texas Tech. I don't feel like they're very different. The the fraction of the students that are really serious students is maybe a little bit higher in Ivy League universities than in some of the public universities, but not all of them. I would say the biggest advantage of the really elite universities, other than the technical ones, which really are more rigorous, is that they have more financial resources available sometimes. And so like they can send students on trips a little bit more easily and things like that. But I think when I was 18 years old, I thought the differences must be enormous. And now that I'm much further along in my career, I think the differences aren't really as big as what often gets made out in the media.
How do you improve your math skills if you love physics but don't have a thorough understanding of maths?
Okay, that's a great question, because math often is a hang up for a lot of people in terms of moving ahead in physics. And the main thing is to just practice. So one thing that happens a lot is this is kind of related to what I was saying about how to approach learning physics. You should think the same thing about math, which is that don't just think, how do I get to the answer? Really stop and think about why the process that you're following should work. Because a lot of times people try to rush to an answer, and it ends up being wrong more often and taking more time than if you really step back and develop a strategy for thinking about where are you now, where are you trying to go, why do these things work. So I don't think I could give you in a few minutes here a full understanding of how to improve your math skills, but there's an awful lot of things that you can do with just hard work.
Do you think space tourism would ever become a reality?
Yeah, I mean, it started already a little bit. So the Russian Space Agency has been allowing people to get a ride on a rocket, and people are willing to pay a huge amount of money for that. And if you're talking about like people going to the moon for vacation or something like that, that's an interesting question. So I think it probably will become a reality for extremely wealthy people, but I think there probably are just going to be, companies like SpaceX have made launching rockets a lot cheaper than it used to be. But my guess is that it'll always be really expensive. So ordinary people will probably never take vacations to the moon or Mars. But we may run into a point in the future where wealthy people do that a lot more often than they do now.
How difficult was it for you to excel in a university with a grade deflation like Caltech? And how competitive was the environment there?
Okay, so it's a really hard school. So basically, and I think one of the things that was good when I was there was that there was a good sense of community among the students. So almost every student who goes there was one of the very smartest students in their high school. And then they get there and suddenly, we had this thing where we sat on the lawn and the dean came out to speak to us when we were freshmen. And the dean told us this, and he said, now remember, half of you will be in the bottom half of your class. And it kind of is a shock to go into an environment where everybody is just as smart as you or smarter when when that wasn't the case in high school. And so it can be a bit of an emotional challenge for a lot of people to go into that environment. But since so many other people are going through the same thing at the same time, there's a good support network. So you have to work hard. You have to really want to be a scientist to do well at a place like that. But people will help you along. And I feel like the biggest advantage of going there for me is that often there are people that I was an undergraduate student with who know almost anything that I want to know that I don't have the expertise on. So I could just think, oh, who would know that? And I can send them a message on Facebook or send them an email or something. And usually I get a good answer back. Yeah.
What are possible career opportunities for a computer science undergraduate?
So, almost anything in science and technology nowadays involves computer scientists doing things. So if you think about like in the space field, running all of the software that runs a satellite. So in some cases, some parts of the software are actually done by physicists and engineers. And in other cases, professional programmers do it. And in some cases, there's some back and forth. So in some cases, the hard part of writing the software for a space mission is understanding all the physics that goes into it. And so in that case, usually a physicist will do it. In some cases, a computer scientist will come along and make the code more efficient after that's been done. And increasingly in astronomy, we're seeing data mining applications. So somebody with a computer science background who learns enough astronomy may be able to find clever ways to work with the big databases that the astronomers don't. Okay, so those are all the questions that you received. And a lot of the ones that I had cut off in order to go to that also came to me privately. Let me go through, I think, this last one or two. So is it true that people who stay in space are younger than people in Earth? I mean, in looks and age. Okay, so I think what you might be talking about is the twin paradox from special relativity. And the idea is that this is one of these thought experiments in special relativity, that if you have two twins and one is on the ground and one goes into space and flies at a large distance and then comes back, if they're flying at close to the speed of light, time passes differently. I'd have to sit down and work that out, which one is younger. I think the moving one is going to be, the moving one is going to be younger, right? So yeah, so that would be strictly true. And then there's some subtle things about getting out of the Earth's gravitational potential well that change the rate at which time passes, but those are not really noticeable. And so in terms of so if you went up on the space station for a long amount of time, clocks run at a different speed, but in terms of your biological aging process, probably the fact that you're exposed to more space radiation up there would do more harm than any change in the rate at which clocks run would cause. All right. All right, one more. Is there a possibility of a meteor like the dinosaur killing one to come to Earth? So yeah, that's always a possibility. And this is actually a driver for some of the programs where people build these big wide field telescopes and take repeated images of the sky to look for asteroids that might be dangerous. The probability of that decreases over time because the asteroids and meteors get used up, but it's always a worry. All right, next. Is it easy to a high schooler to do research with the access of Google only? So easy. So it should be easy just with a web browser to get some data and look at them. But in order to actually do research, you could learn how to look at images from different satellites. In order to do research, it takes an awful lot more training and experience and knowledge. So if you pick a very narrow niche topic, you might be able to find something exciting as a high school student. But in order to really be a researcher, you really need to go through a bachelor's degree and a graduate degree in order to learn enough to do stuff without a senior person helping you a lot. But you can get a feel for some of the things that researchers do as a high school student just using a web browser. You need a little bit more than Google, but you could do it with just a laptop and an internet connection. Okay, what are good research problems that you think should be solved in the astronomy field? So I would say there's a huge number of problems in astronomy. So it's really a question of what you're interested in. And so to me, I'm interested in understanding how black holes and binary systems form, and understanding how the process of mass falling into them and how the process of jets coming out of them takes place. There are other people, like some of the questions we heard earlier, there are a lot of people interested in finding planets around other stars and seeing if any of them have life. There are people who are interested in understanding all the details of the expansion of the universe. People interested in understanding how galaxies form and evolve. And so these are kind of the big area questions. And then in terms of good small research problems, that's something that, I could talk all day about that, but everybody has their own ideas about the specific problems that they actually want to go and solve. Okay. How much evidence do we have of white holes and wormholes? So I would say observationally none. And I would say the white hole idea is basically dead, because that was something that people invented to support this steady state theory of the universe. This idea that we knew the universe was expanding, but there were people that thought that the density of the universe should stay constant over time. And so if the universe expands, but the density stays constant, you have to find a way to inject matter into it. And that was what white holes were, which were kind of backwards black holes. All right, and wormholes are a little bit different, right? So wormholes are cases where space-time is curved, and so rather than moving in the normal direction, you could jump across. Theoretical evidence, I would say, I think that there's some ideas that there are extra dimensions that I would say there's a lot of theoretical work that goes on them, but I don't think there's a lot of really strong empirical support for them. So, but you could make wormholes, in that kind of model. All right, so what changed the idea about white holes? So what I would say is that the evidence for the Big Bang theory of the universe, rather than this steady state cosmology, the biggest thing that changed the idea was the discovery of the cosmic microwave background. And that's this glow at about 3 Kelvin temperature that comes from the early universe. So that was the first big thing. And then now over time, we've made surveys of the universe. And what we've seen is that as you go further away from us, and hence you're looking further back in time, the properties of the universe really do change. So like most of the galaxies are much likely to be forming a lot of stars if the redshift of the galaxy is between about 1 and 2 than they are for redshifts that are higher or lower. And I think that's about 6 or 7 billion years ago. Right. And so as a result, then we know the steady state theory of the universe is incorrect, because we see big changes in the properties of the universe as a function of time. And so that removes the need for white holes. And I would say there was never really any good evidence for white holes. It was just that, if we think about the solar system, historically people thought the Earth was the center of the solar system, and then we realized that the sun was. And then for a while, people thought that the sun was at the center of the galaxy, and then we came up with better ways of measuring the structure of the galaxy, and we realized that that wasn't the case either. And so there's an idea called Copernican thinking, which means thinking that we're not in any special time or place in the history or location in the universe. And so when the Big Bang Theory was first proposed, it suggested that the universe had a fundamental beginning. And some people thought that was a non-Copernican idea and they didn't like it. And so they proposed ways to have the universe expand that were Copernican. But now we realize that the universe really does have a beginning. Okay, so what GDP I need to apply to astronomy, astrophysics, and data analysis majors in the top university? So I think you mean grade point average, I think. I can't give you a good answer to that because it depends on a whole bunch of other factors. So for the top American universities, they'll really look holistically at your application, like what your grades are like, what your standardized test scores are like, essays that you write, and recommendation letters that you get. In Europe, a lot of times you get admitted by a department rather than the university, and then I don't know the process there as well, except for in Britain. And in Britain, it's entirely based on entrance exams, but it varies a lot from university to university. Okay. All right, so I think I've answered all the questions now. Does anybody have any last minute questions?
I think that's all the questions.
Okay.
Thank you so much, Professor, for taking the time to speak today. We really appreciate it. And I'm sure that many students found this webinar to be very beneficial.
Okay, I'm glad you enjoyed it, and thanks for your attention and your enthusiasm and asking so many great questions.
Have a great day, everyone. And you can access the college preparation resources by texting us through email or WhatsApp, the word webinar 2020, and we will get those college preparation resources out to all of you. Thank you so much.